Hi, everyone. Welcome to lecture 5. So today we'll actually get into neural networks. Before we go into the content, just a reminder, project 1 is out and it's due 1 week from now. The auto grader, I got an email from the CSC help desk just before the class that they have set it up, but I need to do testing and also set project 1 for you to upload. So give me like a day or two to set that up. And mostly by the end of Thursday, you should have AutoGrader to test your solutions. We'll see how that goes. Yeah. So it's due 1 week from today. If you haven't started, please look into the instructions and get started, because it might be a little difficult than the project 0. So the sooner you start, the better it is. Okay. So recapping from previous lectures, so we discussed what is linear models. We saw that from 3 different viewpoints: algebraic viewpoint, visual viewpoint, and also like geometric viewpoint. We talked about loss functions. We saw how it prefers different W's. We saw regularization and how it can help you think about test data, not just like overfitting on the training data. And we saw in the last lecture, like optimization routines and stochastic gradient descent in particular. Today, we'll actually go back to the first thing, like classifiers, and talk about how we can do much more than what a linear classifier can do. So let's look at the limitations of the linear classifier. So again, to recap, they are not powerful. For instance, in this particular case, you don't actually have a linear separable like data cloud. So it's not going to work in this particular sense. And also, like we saw that from a visual viewpoint, you only have one template that can describe or represent a particular class or a category, because your W is going to be a dimension of the class and the input vector. One solution before we jump onto neural network is to kind of think about how can we change the input space. So one way to do that would be using feature transformation. For instance, let's say you thought about this particular problem and you came up with the solution saying, I'm going to transform this input into polar coordinates. So Cartesian coordinates to polar coordinates, where this particular data points could be linearly separable, as you can see here. So if you know about the problem and if you can actually come up with feature transforms, you might be able to find a good feature space where you can do linear classification. Now, if you look at the same thing again back into the original space, it's going to look like a nonlinear classifier. But you're applying linear classifier in a transformed feature space. So one common feature transform that people have looked at for many years is just looking at color histogram. So for instance, let's say you have the image of a frog. All you are doing is you have this color spectrum. You're dividing that into a finite number of bins, in this case, 10 bins. And then you're just counting the number of pixels in each bin corresponding to that spectrum of colors. So this is one particular descriptor or feature that talks about the entire image. So you're transforming the input image into this particular feature vector. And then hopefully you can do linear classification in that space. Can somebody tell me what you're losing by just like binning the colors into a histogram? Yes. Any of you? Yeah, sure.
Relative positions between the
relative positions. Any other way of describing the same thing? Yes.
The color of the image can be done by information.
The color of the image will change, which means you'll get a different feature vector. But I think you're not, so basically what you're losing here is spatial information. Like for instance, if you rotate or like flip the image, you'll still get the same feature vector. So it's not going to be spatially variant. So you're using the spatial information, but you're still describing the entire space. This could work if you have, if your domain is, let's say, binary images. You're looking at only the door, trying to classify if there's a door or like between a door and a wall. Maybe this will work because door has a different set of colors. The binning could help you classify whether it is a door or a wall, but not more in more general settings. The other histogram that is commonly used or very popular in computer vision is histogram of oriented gradients. This is actually a dual of the color histogram because it throws away the color information and you're looking at the gradients or the edges in a local region of interest. I'm not going to go into the details here, but I just want to highlight like how this is going to look like. So here you actually converted the input into 8x8 regions, and in each region, you have like 9 directions, and you're trying to see like which direction has most. You're trying to see which direction has more strength, and that is what the histogram of oriented gradients actually does. So if you specifically look at, there are regions here that we can talk about. For instance, the eye of the frog, you can see that it has gradients across many directions. So you'll see like strikes along many directions. Whereas on the orange, on the right corner, right, the top corner, there is no gradient from any of these directions. So there is no information from there. So this has been widely used for object detection, pose estimation, and but one thing to remember is this is something that was like explicitly represented by a practitioner or somebody who knew that edges are important. For instance, in the previous case, colors are important. So somebody hand-tuned these features so it can work on image classification. One other feature that is very popular in computer vision community is bag of words. As opposed to the other two features, this is data-driven. So what essentially happens here is you have a training set, and then random patches are drawn from the training set, and they are clustered. So you can have a cluster mean and a cloud of these patches in a feature space. Now, think about if you have an image that is coming in, you can actually create a histogram of how close these patches of this image is with respect to the mean clusters. So that gives you a new feature of the particular image that you're talking about. So this is a different way of describing the image. So we saw color histogram, which did not have any notion of space. It was throwing away spatial information. We saw histogram of gradients, which was throwing away sort of color information. Here we are looking at a much more flexible way of doing this, where it is trying to learn these what we call codebook of visual words from the data, where it's not hand-tuned by some practitioner. You see the difference here so far? So good? Any questions? Yes.
So I'm assuming it's not instantly for exact pixels, right? How does it determine whether or not to put it in a bag?
So it is trying to compute the distance between a patch of your input image and the existing clusters or the existing means of the clusters. So you get a distance and that gives you a histogram. Yeah. And there are many variants of bag of words. In fact, this is very popular that even in the CLIP model, which is more recent, they've kind of used this knowledge of having a common embedding space by looking at bag of words from a language perspective and bag of words from an image perspective. So if you're looking into CLIP paper, think of bag of words and you try to find analogies between the words.
So this also loses spatial information from the degree, or would you say that the pathing in itself
I think the patches in itself has the spatial notion to it. Right, only local. Okay, so you can also use multiple features and concatenate them to give a description of your image. For instance, it could be color histogram, histogram of gradients followed by bag of words, and you concatenate all of them to give one huge vector that talks about your image for doing classification. Right? So we talked about how the feature transform could change the input space into some feature space where you can do the classification. So that's where we are right now.
All these talking about like different features.
They might be talking about different things. They might be able to capture different aspects of the image. So I just gave an example. You can have different, for instance, there are like features like surf, sift, and so forth. You can have different features and like use them together for describing an image. Yeah. So before deep learning hit the deck, like we had we'd used all of these features in one way or the other. And especially in 2011, in the ImageNet challenge, before AlexNet came into picture, they used SIFT features, color features, and reduced the dimensions to 64 using what we call principal component analysis, which is basically dimensionality reduction approach. They also extracted Fisher vector feature and then compressed that as well. And at the end, you can imagine using all of these features, they used SVM, which is support vector machine, which is a linear classifier, to classify images. And this was like the state of the art back then in 2011 before AlexNet or a neural network came into picture. So again, we are talking about feature extraction being a standalone process before we do classification. Yeah, I think that's very important to think about. So before we get into neural networks, you want to understand like what is a key difference between neural networks and what was happening before. So here is an illustration. So you have an input image, and there is a process of feature extraction. Like I said, you can do color histogram, histogram of gradients, or use multiple feature extraction techniques to combine them to give a particular feature. And then you're using a function f, which is your classifier. That is where the training is happening. So you can do stochastic gradient descent to train the classifier to label classes, right? So the feature extraction is different from your classification. That's what was happening before. And if you're looking at neural networks, you're looking at an end-to-end system that takes in the input image. And while it is extracting the features, it is also thinking about optimizing the classification problem. So that is a key difference between the earlier approaches and what neural networks is doing. So the feature extraction is no more a standalone process. It is actually happening along with optimizing for your classification performance. Yeah, is this clear? Okay, so if you want to like formally talk about neural networks, first of all, let's think about linear classifier. The input is d-dimensional vector. Yeah, output is c-dimensional vector, where c is the number of classes. Linear classifier is a linear combination of W and B, where W is the weight parameters, B is the bias. And W and B are the learnable parameters in this case. Yeah. Now, if you think about two-layer neural network, it is going to have similar, so it might appear similar to what you see in the linear classifier. So two-layer neural network has two Ws, W1 and W2. Where if you think about it, this part is the feature extraction, followed by the classification at the end. Yeah. You can also think about this to be the X in the linear classifier. Now you can imagine if you add more layers to your neural network, this would be a recursive process, assuming that all these layers have same activation function. We'll talk about activation function, which is kind of induced here, saying a max of thing, but think of that as some function that is acting as an activation. Pictorially, you will see these images in the papers. You will see these block diagrams in the papers when they're talking about neural networks and architectures. So the solid or the blue colored blocks here are the vectors. So you have input vector, hidden vector, and then output vector in this case. You can stack many layers and that will form your deep neural network. One thing to note is that, so the weight matrices actually determine how a particular element in the previous layer would influence a particular element in the next layer. So they kind of determine how much the influence is. That's what the weight is actually talking about. But in this scenario, if you pick one of them, like let's say on the left side, the element I, j of W1 has an effect on HI, like how much like XJ influences HI. So that's what it's talking about. Similarly on the other side as well. So in this particular scenario, let's say W1 and W2 are very dense matrices. What we are talking about something that is called fully connected network, or in other words, this is also called multi-layer perceptron. Do you remember perceptron in the first lecture that came in 1950s? So MLP, so multi-layer perceptron nowadays is commonly referred to as MLPs. Like people talk as if it's its own thing. So if you're hearing MLPs, you want to like make sure that okay, you know that that's a fully connected neural network. It's not a CNN where all the elements are connected to each other. Something to remember by. Very, very commonly used. Any questions so far? Yes.
Is there a synonym for FCM?
Yeah. Fully connected neural. Yeah, they also call it FCN. Yes.
FCMs are fully convoluted.
Really?
It's like convolution only without any fully connected anything.
Okay.
That was like confusing for me too, because I always thought it was like fully connected. So like everyone was like, oh, these are just like fully convolutional image like models, like resonant.
Interesting. Maybe you can look it up and like make sure what Ku said is correct. But I'll trust him. Okay. So we saw that in the linear classifier, we were able to visualize the weight matrices and said like each row of the weight matrices actually can be transformed into image. It talks about the template or a representation for a particular class. So can we do that for the neural networks? We can, but it's hard to kind of see what is happening. So this is what we collected for two-layer neural network, especially for the props dataset. What you can imagine is the first layer is a bank of templates, and the second layer is trying to recombine these templates to do a classification. So what you're seeing on the left here is image that is from W1. That is why you have more number of templates than the number of classes. The number of classes were actually 10 in the props dataset. Yes.
Sorry, what do you mean by?
So in the linear classifier, the W matrix, we saw a visual representation as earlier here, where we can say, okay, we can take the row of a W matrix and convert that into an image, which were looking like these templates. And because we had like 10 cross the size of the input vector or the size of the input image, we could just visualize that as an image And they were only 10 in number because of the weight matrix. Whereas in the 2-layer network, we can imagine that you have more templates that would later be combined to do the classification. So here, it is hard to pick examples, but I'm just doing. So if you see the ones that are highlighted with red bounding box, looks like the tomato soup can, but they are completely different from each other. So maybe they are like trying to represent two different aspects of the tomato soup can. Same way, the mustard bottle. So one is dark in color, the other one is bright. So maybe they're trying to represent the illumination changes in the data set in a way. So again, like I just picked and I'm like coming up with my own explanations, and it need not be like what it is actually doing there. But it is nice to see that there are different templates that later combines to do the classification for you. Yes.
So when we say that H is 100 layers or 100 wide, is that you have 100 templates or?
Yes. Yes.
Okay.
So it depends on the size of the W1, right? Like if you're visualizing W1, the W1 takes X. So the dimensions of W1 is, let's say 100 cross 3072. So you can generate 100 images from that. And those are the templates here.
Yeah.
Okay. So deep neural network is basically stacking of all these layers. And if you want to write it mathematically, this will look like what we saw earlier. It's a recursive function of the same thing that we saw earlier. And generally, it's good to learn about or know about what people mean by depth. Depth is actually referring to the number of layers, whereas the width is referring to the size of each of this layer. So there are properties. We'll see that later in, I think, in a couple of lectures from now, where we'll talk about like how much influence has the width made or the depth made to the ImageNet classification challenge. Like you'll see like few networks that came into picture where by changing the depth and the width, they achieve different properties or different results. Okay, so let's get into activation function. So we saw the max thing that I said, like, let's talk about later. So we'll talk about that here. So activation function will actually transform your linear value into a hidden value in a non-linear fashion. We're not going to use a linear function. It will be a non-linear function most often. And in this particular case, we are going to talk about the ReLUs, which are called rectified linear units. So before we jump into activation function, can you think about what if we did not have the max function? If it is, let's say, just like W1x plus B1. Exactly. So this will be a linear classifier again. This is often called deep linear networks. While it is not of interest for people who are doing image classification or like any computer vision task, this is actually of highly relevance to people who are doing optimization. Apparently, it gives you complex optimization characteristics, and they are interested in like studying that. So if you think about, if you want to name this particular kind of networks, these are called deep linear networks, where the activation is actually linear. Okay. So there are many activation functions. We will look into some of these in the next few lectures. But most commonly used is the ReLU. And for your project, in the later projects, you should be using ReLU as your activation function. Or for any other future projects, if you're thinking about building your own neural network, you should start off with ReLU before you look at other variants of ReLU. Okay, so neural network, you can write the code in less than 20 lines. And the basic elements here are like, okay, let's initialize the weights and like get the data. And once you have the data, figure out, you iterate through the optimization. So there is a for loop, and then you compute your loss. Let's say in this scenario, it's a sigmoid loss. Sorry, sigmoid activation and L2 loss. Then you compute gradients depending on your labels, the labels from your data set already. And then finally, you need to update your weights, which uses the SGD step. So in a nutshell, this is a stencil for writing a neural network code. But in practice, like if you're looking at different data sets, there are data loaders. You will see like much more complex codes. But in a nutshell, you should imagine that this is what is happening behind the hood. So neural networks are very good at doing or approximating functions because they do something called space warping. Space warping, let's understand it more from a geometric viewpoint. So this should be familiar to you. Like we saw this in a few lectures before, right? When you're talking about linear models. So consider a linear transform where you have h equal to w times x plus b. And in this particular case, imagine x and h and b are 2 dimensions. Right? So let's say you have x1 and x2 for your input. And you have 2 linear planes that are actually going through the wall right now. That kind of classifies into 2 different labels. So you see the red color. So you see that we saw this earlier, right, in the previous lectures. So if you are on this line, we are talking about the templates from your weight matrices. It's going to be more closer, or the dot product is going to be super high if you are moving along this direction with respect to this particular class. The same way on the other side. We also talked in like few slides before that it is good to think about feature transformation. So if something is not linearly separable in the input space, can we do a feature transformation? Now let's see what happens if you do a linear feature transform. It's going to look like this, where you have H1 and H2, which are kind of orthogonal to each other. And the quadrants, so for any data that is here, which is on the positive direction of your H1, sorry, H2, positive direction of H2, and negative direction of H1, you'll see B in that location. So the quadrants in your original space is being transformed into linearly separable regions in the feature space by just using one transformation. Yeah. Now let's look at this by using a cloud of points or cloud of data. So this is going to look like this one. For instance, to be very specific, you have these 5 points here that is being populated in this location. But again, it is still not linearly separable in the feature space. We talked about, okay, can we do a feature transform using a linear function? And what happens to that? Right? Now, let's look at what a ReLU would do. So the ReLU would actually, because for a negative input, your output is going to be 0. For positive input, the output is going to be the same as the input. You can imagine that the B here, which has positive on the H2 direction, negative on the H1 direction, will all collapse on this particular line, right? Because this value is 0. Yeah. Now you can imagine the D also does the same thing. D from the input space with positive H1 and negative H2 would collapse to H1. Can anybody say what will happen to C? Let's say C is here. It collapses to the origin, right? So if you look at the same thing using the cloud of data that we had, so this was what we had when we did linear transformation. Now, if you use ReLU, which is a nonlinear transformation, they kind of collapse onto the axis and the origin. Now, if you think about it, this is linearly separable using a classifier, linear classifier, which means in the original space, this is a nonlinear classification. In other words, what is happening here is there are multiple linear classifiers in the original space holding your data such that you have a folded transformed space, folded transformation in the feature space where you can apply linear classification. Yeah. Now so we have we are only considering two units in your hidden layer. The idea is if you have multiple hidden units in your hidden layer, let's say the input was only 2-dimensional, whereas your H was like 4-dimensional, 5-dimensional, or 6-dimensional. The ability to do the linear classification would be higher, or the classification is going to be much more accurate for a complex input data. So one way to think about it is, if you have 3 hidden units, you are doing classification, but you might have some sort of inaccuracy. But if you increase the number of hidden units, your representation is going to be much more, much better, that you can do, you can get higher accuracy. Now, this is somewhat alluding to what we had like with the k nearest neighbors, and also like the idea of overfitting. So you should be able to connect like, okay, is it good? Should I add regularization somewhere? Is it going to be some of the weights in the neural network? But I think the right way to do the regularization here is not to think about like reducing your hidden units, because one can say that you might prefer this one over this one because that is not overfitting and this is overfitting, which means you want to reduce the number of units in your hidden layer. But instead of doing that, you can keep the representation, but have a regularization as an additional term where you can tune the strength of your regularization to have the same property. So these plots are basically generated using this web applet or a JavaScript applet that was created by Justin Johnson. So I would highly recommend you to go and play around and see what happens when you're changing the number of hidden units, activation function, and how that affects your decision boundaries. Any questions so far? Okay. Silence is good or bad, I don't know. Okay, so neural networks are generally, you can think about them as function approximators. How good they are is debatable. Sometimes people have worked through examples to say that they are good approximators. One thing that commonly will come across is that are they universal approximators? So one can say that neural network is a universal approximator, even if you have one single hidden layer, and it can approximate any function. Again, this is debatable, like I don't want to go into the weeds of it, but you can say that it can do this with a bound on the inputs. We will talk about like why you should be very careful about this notion of universal approximation and not just believe to the expert that it can approximate everything at few slides from now. But let's like maybe look at some examples to start off and understand this concept much more detailed. So let's say we take a 2-layer ReLU network. And for simplicity, we are going to consider the input to be one single value, the output to be one single value. And we'll have 3 different hidden units, part of the hidden layer. So one hidden layer, which has 3 different units. Just to be clear, layer is different from unit. So we have one hidden layer, which has 3 different units. Yeah. And this should be 1, 3. That's my mistake. Okay, so you can write the output for each of the hidden unit as, let's say you're using, in this particular case, ReLU function. So you can write maximum of 0 or W1x plus B1 and so forth, right? And then the output is going to be a linear combination of all of this. You can also write that in a different way. You can say it's a linear combination of a scaled ReLU function. Same thing, right? we're just like reformatting that into a different way of writing it. So it's a linear combination of scaled ReLU network. What this can actually do is you can approximate a linear piecewise function such as this one, where it can be thought of as a sum of shifted ReLUs or sum of shifted scaled ReLUs. So the position of the bend will be determined by your BIs, and the slope will be determined by your the UIs and XIs. So for example, let's say we are looking at a bump function that is like this. This can be approximated using 4 hidden units in one hidden layer. For instance, you can have a summation over 4 different ReLU functions that look like this to get that particular bump function. Right? We are approximating a piecewise function using a bunch of hidden units. Right? Where you can think about the scale will be different, the parameters inside the function will be different, but you can still like approximate this particular bump function. Now imagine you have some arbitrary function and you can use many hidden units. You can approximate many different bump functions. For instance, let's say you have 4K hidden units. If we are able to approximate this with 4 hidden units, you can approximate this K bumps using 4K hidden units, right? Makes sense? Now these bumps are basically approximating a different function altogether. So that's where we're alluding towards a universal approximation using neural networks. There are like a lot of questions here that needs to be investigated or like looked upon in detail. For instance, what happens between the bumps? Are there any other nonlinearities that we are not talking about? Are these high-dimensional functions and so forth? So I'm not going to get into the details, but there are like pointers to that on the slide that I'll leave for you to look into. But most interestingly, the thing to understand here is it does not actually learn the bumps. For instance, let's say we are trying to approximate a sine function. With large amounts of data, it can actually kind of approximate that using a piecewise where you have inputs from all these hidden units that are helping approximate that particular function. So it's not actually really learning these bumps to some extent. So the thing to note here is that you can think of neural networks to be a universal approximators, but you don't actually really know how to train or how to get the weights to approximate a particular function that you have. It might be really hard because you don't know what is optimization routine to use, or how much data do we actually need to get to that stage or to approximate that function. So while it has the ability to do that, we have seen that empirically, but but we do not know how to get that particular function approximation. Does that make sense? So it is a universal approximator, but we do not know how to approximate a particular function because we have no sense of like how to do optimization in that particular landscape. Or at the same time, we do not know how much data do we need for it to be a perfect approximator.
For Canon, how do we know that we can approximate?
Similar properties, right? So KNN, if you think about the data, if you have large amounts of data, it's basically memorizing everything. So you should be able to approximate. So that's why it's called universal approximator. Yeah. So let's, so I'm going to give you a little bit of introduction to convex functions, or how to think about what is a convex function. Because like we'll talk about this either in the papers or in the future lectures. So I think it's nice to understand what we mean by the property of convexity. So let's talk this visually. So basically, when you satisfy this particular expression, then the function is convex. The left-hand side of this function is talking about this blue region after taking x1 and x2. So you sample 2 points in your input space and try to see like what are the values that are produced by your function. On the right side, you're basically talking about this line that is joining these 2 points in your input space. And at every point in the input space, that should be higher than your actual function value, right? So that is the definition of a convex function. Yeah. So example for where it is not a convex, this one. We have this line, but these values are above the line. So a nice way to think about convex function is that it's a multi-dimensional bowl, which means you have only one local minima. Yeah, if it has like many local minimas, then it's not a convex function. So if you are defining convexity at a particular interval, sure, then it should have only one minima in that interval. So it depends on how you define convexity. If you're defining convexity for the entire space, then it should have only one minima. So the thing to know about convex function is that it's easy to optimize, and we'll always converge to a global minima. So the functions that we talked about in linear classifiers are convex functions, and that's why like people like to use linear classifiers, whereas neural networks are not convex. So here is a slice, a 1D slice in the landscape of 4-layered Rayleigh network. So here it looks like convex-ish in that particular one-dimensional slice, right? We have multi-dimensional input, so we are taking particular slice of that input dimension. Here is another slice where it's definitely not convex, and you can see like various characteristics at different slices. So yeah, so neural networks need non-convex optimization techniques, and there is no guarantees that it will converge, but they work empirically. I think that's why we are in this course, and it's an active research area where people are studying about these properties of neural networks and how they are working. Okay, so in summary, we talked about feature transformations, and then we talked about the difference between earlier technique where the feature extraction was a standalone process before we do the classification or any computer vision task, and how it compares to neural networks, which thinks about it as an end-to-end process. We looked at fully connected networks. And we also saw the comparison between the templates and a visual viewpoint. How can you compare with linear classifier and the neural networks? And we talked about space warping and the property of universal approximation, and also a little bit into like what we mean by convex function and non-convex functions. So we still haven't discussed about how to compute the gradients in a more structured way that you could train your neural network. And we will do that in the next class on where we'll talk about backpropagation. I think that is the end of the lecture.